Hey everyone, welcome back. You are tuned in to an explainer from the Foundry by Forge College. I'm your host, and today, man, we are really rolling up our sleeves for a true engineering teardown. We're going to look at the exact microscopic gears powering blockchain fundamentals. Think of this explainer kind of like taking apart a finely tuned mechanical watch just so we can see exactly how all those springs and cogs actually work together.
So, in our previous lesson, which was on the foundations of HD wallets, we talked about the big picture, right? We covered why we use mnemonic seed phrases and how they conceptually map out into this massive, sprawling tree of accounts and addresses. But honestly, that leaves a pretty massive, fascinating question on the table. How exactly does one single seed mathematically generate an infinite, completely reproducible tree of keys? Well, okay, let's dive right into this and open up the black box. Here's our technical blueprint for today. First, we'll open that black box, then meet the core derivation engine. We'll explore the hardened versus non-hardened fork in the road, explain extended keys, and wrap it all up with some real-world wallet applications. Don't worry, you won't need a PhD in cryptography to turn these gears. All right, Section 1. Opening the black box and zooming in on the mechanics. Okay, so everything, and I mean everything, revolves around this beautifully simple equation. Parent key plus a chain code plus an index equals a child key. That's it. That's the core equation of our entire derivation machine. You feed these three precise inputs into the system, and it'll churn out a deterministic child key every single time. It's kind of like a strict cryptographic recipe. If you use the exact same ingredients, you're going to bake the exact same cake, no exceptions. Let's see how this actually builds our system.
Moving on to Section 2, the core derivation engine. It is time to meet the crypto blender. Meet our engine. It's called HMAC SHA-512. Now, I know that sounds like a terrifying piece of military hardware or maybe a fancy barcode scanner, but you can actually just think of it as our highly reliable crypto blender. It takes our inputs, turns them on high speed, and blends them into a perfectly predictable 512-bit output. It is just a one-way mathematical function, but it literally drives our entire derivation process. But, I mean, a blender needs power, right? And that is exactly where the chain code comes in. A chain code is a 256-bit packet of what I like to call entropy fuel. This fuel is attached to every single node in our key tree. And why do we do that? Well, because we need to derive children safely without leaking the actual private key material. The chain code adds that absolutely crucial cryptographic randomness, the fuel, that keeps our engine running securely at every single branch.
So what actually happens when we hit the blend button? First off, we compute the HMAC SHA-512, which spits out a massive 512-bit string of data. Then we take a mechanical cleaver and literally chop it right down the middle. The left 256 bits, that becomes the integer tweak we use to derive our actual child key. And the right 256 bits, that becomes the brand new chain code for the child, completely ready to fuel the next generation. Oh, and by the way, the official standard does note that if the left side results in an invalid curve order, the process fails. But honestly, the mathematical probability of that happening is so vanishingly small, you literally have a better chance of winning the lottery while simultaneously being struck by lightning.
Which brings us to Section 3, hardened versus non-hardened, the fork in the road.
Just take a second to think about this absolutely massive number, 2,147,483,648. Now, mathematically, this is just 2 to the 31st power. But in our world, this exact number is the absolute index threshold that flips a key derivation from non-hardened to hardened. In wallet development, we usually just denote this with a simple little apostrophe, like 0 prime. If your index hits this magic number, the entire mechanical behavior of your wallet just flips. Now, what's really interesting here is the specification matrix between these two modes. Think about the data input for a second. This is the tiny but absolutely critical difference. Non-hardened derivation feeds the parent public key into the crypto blender. But hardened derivation, it prepends a 0 byte and feeds the parent private key into the blender. And because hardened uses the private key, you literally cannot derive its children if you only have public information. It acts as a rock-solid cryptographic firewall. If you expose a non-hardened public key, yeah, people can see your child public keys. But a hardened child, it remains completely hidden and totally safe, even if the public information gets exposed.
All right, Section 4, Extended Keys Explained. How we package up all these gears.
So we package these keys up as extended keys, completely serialized into a format that we can easily export. Here's the ultimate matchup, XPub versus XPRV. An XPub, or public extended key, contains the parent public key and the chain code, but it can only derive non-hardened child public keys. It's essentially public, view-only magic. The XPRV, on the other hand, the private extended key, well, that holds the parent private key and the chain code. So the absolutely crucial takeaway here is that an XPRV can derive literally everything, all hardened and non-hardened child keys all the way down the line. It really is the master key to the castle.
Which brings me to a golden rule that I need to deliver with the utmost seriousness. Listen closely. Never hand out an XPerv or any private key material. Ever. I mean it. Possessing an XPerv means you have total, absolute control of all descendant funds on that branch of the tree. An XPub, sure, that's totally safe to share with an auditor or maybe a tax app. But an XPerv is for your eyes and your highly secure cold storage. Only. No exceptions.
And finally, Section 5, Real-World Wallet Applications, Building the Code.
What you are looking at here is the standard path layout you'll see in almost every single modern wallet. M/purpose prime/cointype prime/account prime/change/address index. Do you notice those apostrophes? Yep, those are our hardened keys. We harden the purpose, the coin type, and the account to strictly isolate them. That way, if someone somehow gets your Ethereum account public key, they can't use it to reverse engineer your Bitcoin account. But notice that change and address index at the very end don't have apostrophes. They are non-hardened. This is brilliant because it allows us to use view-only replication to generate thousands of receiving addresses effortlessly without ever touching our private keys.
Let's quickly talk through the pseudocode logic of how a wallet actually boots up. Step 1, you convert your mnemonic phrase to a seed. And yes, pretty much every developer tests this using the infamous abandon mnemonic phrase, which, for sure, you should obviously never use for real funds. Step 2, we create the masternode from that seed. Step 3, we derive a hardened child using that massive 2 billion index number. Step 4, we derive a non-hardened child using index 0. And finally, Step 5, we export those child public keys so we can actually interact with the blockchain. It's just a perfectly reproducible machine. Let's just do a really rapid recap of the 3 core principles we've covered today. Number 1, the HMAX SHA-512 crypto blender drives every single derivation step. Number 2, the difference between hardened and non-hardened is literally just a mechanical difference in what data we input. And number 3, exact inputs guarantee 100% reproducible outputs. By the way, actually applying these mechanics hands-on is a huge part of the courses and learning programs you'll find over at Forge College. It's really where all this theory finally meets practice. And this brilliantly illustrates why all this raw math actually matters in the real world. Watch-only custodial wallets, they're made possible entirely by non-hardened XPub derivation. Think about it. You can keep your private keys buried deep under a mountain somewhere in cold storage and simply export an XPub to your everyday phone. Your phone can monitor your balance, it can generate brand new receiving addresses perfectly, but it never ever has the ability to spend a single cent. So I'll leave you with a bit of a provocative thought as we wrap up this explainer. Is your local development environment actually ready for programmatically managing multiple accounts? Because in our next lesson, we're going to start writing the real code that actually turns these gears. To prepare for that, and to dive way deeper into this subject and a ton of other fascinating Web3 topics, make sure you head over and visit forge.college to learn more. Thank you so much for joining me on this teardown, and I will see you in the next one.